Hello everyone. So thank you for choosing this session where you're probably not going to learn anything for your daily job. I mean, if you wanted to, you could have gone to Josh Long's Spring Boot session, but probably less interesting, right? You know everything about Spring already. So, do you like science? Yeah? No? I hope so, because today we're going to do some real science. So how many of you are already astronomers, amateur astronomers? Nobody? Okay, so this is going to be fun. I hope so. So we're going to produce images like that, images of the sun. So my name is Cédric Champeau, so I work at Oracle Labs on the Micronaut framework. Today my main focus is around everything around the build plugins, developer productivity and things like that. So I used to work for Gradle. Typically, I used to work also on Groovy, the static compiler for Groovy, etc., etc. And today, my session is not about work. This is really about my passion, which is astronomy. And I'm, well, amateur astrophotographer. So if you want to have some pictures like the one on the screen right now, which is quite good on 4K, right? You can actually follow me. I'm not on Twitter anymore, or X, whatever it's called. You can follow me only on Mastodon. So I have a couple of accounts. One is just the first one is my account for work-related stuff, and the second one is just dedicated to astronomy. So depending on what your focus is, you can choose. All right. So we're going to talk about this project, which is called the JSol'Ex project. And JSol'Ex stands for Solar Explorer. And we're going to really see in that session why we talk about exploring the sun, right? So this device was actually invented by the guy in the picture, whose name is Christian Buil, so a French famous astronomer, amateur astronomer, also working on professional and amateur projects, so they collaborate together, and we're going to see that later. And this project is really something free, so you have everything at hand and you can do it yourself if you want to. So I have the device here. If you want to take a closer look at what it looks like and what it can do, come see me after the session. It's going to be easier, but you have that in the picture right now. And when I started with this project, basically I started, I think, back in April this year. I was only doing some what we call deep sky imaging, so really pictures of the galaxy, nebula, etc., etc. And I was not into solar imaging at all. And one of the issues into going with solar imaging is that you have to buy a lot to get into that. Well, traditionally, you have to buy a lot of things, so it costs a lot of money. With this device, it makes things much cheaper. So I'm not saying that it is cheap. Like, for the complete package, you would get around 1,000 euros, right? But it is much less expensive than anything else you would find in the traditional astronomic world, right? So there's a link to the project there. I will post the slides, obviously, so don't hesitate to take a look after. There's a gold mine of science in there. So this device actually doesn't work alone. So this is actually photos which are from a couple days ago. So I was actually in the south of France in a base camp, like astronomy, just with this device, and this was the first meeting in the world with many people having the same device, so this JSol'Ex device. And actually, I don't know if some of you already have some typical photo, like a Nikon objective or whatever, teleobjective. Actually, you can use that device on that too. So you don't have to go with specific things like a refractor. So the first picture, you have a refractor, and then the device is at where you would put the ocular traditionally. So you have the first one is a traditional refractor. The second one is actually someone with a teleobjective like the Nikon one. And the last one, I found that it was funny because you see that the mount is actually very, very close to the ground. So he had to put himself in this box just because of the light of the sun to protect the screen of the laptop, etc., etc. But even with really, really cheap devices, you can do some real good photos. And the question is, how do we get to that? So, this is the kind of photos that you can get with this device. So this is really, well, these are actually photos I took myself. I will show you other photos I didn't take, but this is real science. And what you get on the left is a photograph of the sun in the H-alpha ray. So it is a very specific narrow band image where you can see everything around the activity of the hydrogen ray, right? So the sun is basically a ball of gas. Most of it is hydrogen, and what you would see there is the activity in the hydrogen spectrum. So you can already see some nice things like filaments, so these kind of dark things that you see there, right? And on the limb of the sun, what you have is protuberances. And these are actually exactly the same as these filaments. It's just that you see them going in your direction instead of being on the opposite direction, like orthogonal direction. So what you see there is exactly the same as what you have there, except that it is just a spatial dimension change, right? So we can produce some things like what you would get during an eclipse. So this one is just a virtual one that we can produce with the software. And the last one there is much more challenging to get, and that's one of the really super interesting aspects of this project. This is an image with the helium line, and this one is something which is traditionally not seen in amateur astrophotography because you don't buy a filter just for that, and it would be very complicated to get an image like that with a typical hardware that you get in astronomy, right? So I'm going to show you later how you can produce such an image and what it involves, and that's exactly what I wanted to learn when I started this project, so JSol'Ex. So other images that you can get with the same device. So on the left, what you have is yet another spectral line. So this one is calcium, and you can see already different structures on the sun. So not the same filaments, you can still see them, but there are other structures coming. And this is also exactly why we are calling that device a solar explorer. Because basically you can, with this device, just by moving a small wheel, select the wavelengths that you want to explore, right? Without having to buy many filters, each for the different wavelengths that you want to explore. On the right, it just shows that even if you go with a long focal length, you can really zoom on the sun and get super nice details. So this is really something which is cheap, provides many different advantages of typical filters, and lets you basically use what you have at hand and complement that so that you can produce nice images. These ones are becoming really challenging. So I personally didn't get to producing such images. So you won't get the images on the bottom there, but you should focus on the ones on the top, right? So these are basically the images of the sun corona, and this is what you would get if you have a real full eclipse, right? Something which happens maybe every 50 years in your region, if you're lucky. I have never had the chance to see a full eclipse myself. Maybe in a couple of years in Spain, if you live in north of Spain, you will have the luck to do that. But this is typically what you only see in that circumstance. And it is actually possible to produce an image with this device, which weighs about 200 grams, not much more, to produce images of that corona. And it is basically the comparison with what you would get on the bottom with a satellite, which is, well, not in the atmosphere, so much easier for it to actually have some images. So really nice. And the last one I want to show, and again, this is my next target, next challenge with this. This is what we call the magnetogram. And there what we are seeing is the magnetic activity of the sun. So you have, these stains like black and white, and these correspond to areas where the magnetic field is either positive or negative, right? And you can see actually the activity of the sun. And what is actually really amazing is that just with this device, you get something on the left which looks almost identical to what you would get with this professional dedicated satellite, which is $1 million, if not more. Yeah, you can do that at home with just this device plus 3D printed parts. And I don't know if the movie tomorrow is going to be in 3D, but basically what you need is 3D glasses that you're going to cut just to get these polarized windows. So it's really amazing that you can get to do some real science and actually contribute to the research just with this small device. So the last one that I want to show you just using these slides is also another way to put it into action, and that's an animation of the sun, but not a typical one in time. This one makes you travel between the different levels of the sun's atmosphere. So you're basically moving either down or up. So if you move down, you're going to be to the chromosphere, so something that you would see with the eye, and that's mostly white. And you see these dots, dark dots, which are actually areas of the sun which are colder than the average. So we're talking about something like 4K Celsius in general, and the dark dots are basically like 500 degrees less. So it's still hot, but cold enough so that we can see that. And this animation is basically moving from this visible spectrum to something that we cannot see, which is this H alpha thing, right? So we're basically moving into the atmosphere and looking at different things in a single animation, and this can be produced with the software. So the science behind that is, of course, the nature of light. And if you remember your physics courses, so I know that Stefan this morning said that there was physics at Devox. Yes, there's physics on Devox, and that's a part of physics. And this is the part of the light, the spectrum of the light, which is the visible spectrum of the light. So this is typically what you see when you have a rainbow, right? So it is exactly the same principle. We spread the light, and then we're going to look at a particular wavelength. So when we were looking at the first image, so if you remember the orangish one, that's the C line, which is called the H alpha line, and it's closer to the red. And when I was showing you this purple line, so the calcium line, you are in closer to the ultraviolet side of the spectrum of the light, right? So depending on what you want to see, you basically move this, and you can select what you're going to see. So it's really interesting to manipulate and see that, and the whole science is just in this small device is just to select and do something so that we can produce an image. So when I was trying that, I was like, I don't understand how this works. Like, how can I select a particular wavelength and then produce an image, etc., etc.? So this is really about that. So just for you to understand a bit better some of the benefits of the project, I'm just reminding again, maybe you still remember from your classes. So an angstrom is basically 10 nanometers. So that's the unit that basically opticians use and astronomers in this specific area use to talk about the wavelengths of the light. So what are the benefits of using this project? So first, yeah, you can select the wavelengths. But the second one is probably one of the most impressive things that you can do. So with this small device, and if you remove the camera, it weighs about 200 grams, not much more. You can actually have a resolution which is less than 0.2 angstrom. So if you're familiar with astronomy, and of course, apparently not so many people are aware of that, if you actually buy some filters, like let's say you want to do H alpha, you would buy a filter. That filter can cost you from 1,000 to 10,000 euros, right? Just one filter for one wavelength. And the resolution you can reach is not that narrow. It would be something like 1 angstrom, not more, right? And actually because of industrial processes, and that's the reason why there's so much difference between the price of the different filters, depending on the industrial process, they cannot guarantee the width of the filter, that it's going to be narrow enough, right? So with this device, you can actually have something which is very narrow, so you can really see that particular wavelength and nothing else. The second thing which is interesting to mention is that you are again doing real science, and that science is called spectrography. And you can evolve this device from something which would look at the sun to something which would look at the stars. So you can buy an upgrade kit, and when you do that, you're basically doing some spectrography of the stars, and that would let you do at home something like figuring out what is the composition of the star that you're looking at. Like, is it made of, does it have, I don't know, calcium or whatever. So you can determine exactly what you have there, and there's nothing closer to science than that, right? This is exactly what scientists are doing. Like all the expensive telescopes that you have already on Earth are doing that kind of thing. Problem that we want to solve with this, you're gonna have a direct image of the sun. This is not possible, and we're going to see why. So while it has some benefits, the problem is that you cannot put your eye and look at the sun, right? Or you cannot put a camera and take a picture directly and see that sun, right? This is not how it works. So if you want to do that, well, you buy the filters or you buy dedicated devices just for that particular use case, but you won't get that. And that's exactly why we need software there. So we're going to need to reconstruct an image, and we're going to see what it means. So there's one official software, which is called INTI, and it was designed by Valérie Desnoux, who is actually Christian's wife, so it helps. So he has the expertise on the hardware, and she has on the software. And I was with her just during that bootcamp a couple days ago, so that's the picture you get there. And behind, you actually have my telescope with this device there. So that's the official software. And why we need software? Because the device that you have there works like that. So again, this is exactly the same thing that you have there, except that it is reversed. So I can try to put it in the same direction. Let's do it like that. So you have light coming in that direction. And then here you have a slit, very narrow slit, like 10 microns. So it's really something that you can see with the eye. But that slit is responsible for just capturing a single line of the sun. So we're going to scan it line by line. That's basically what it means. Then you have this collimator, which is going to put all the light which is focused on the slit, spread it and move it so that all the lines are horizontal, and then it would hit what we have there, which is the most critical part of this device, which is called the grading. So there's a holographic grading that has 2400 lines per millimeter. So this device is responsible for doing this spread of the light into its spectrum, right? So we're going to see that rainbow. This is the device which is responsible for generating that rainbow and spreading the light. So first we have the slit, which selects one line of the sun, and then we're going to generate a spectrum from that. And then the last part is take this spectrum and focus it onto the camera, which is there. And then we're capturing something. And what we're going to capture is videos. And then we have to rebuild something, rebuild an image. So how it works is basically like that. So the bar on the left is, the gray bar is basically the slit that you have, and it's going to capture images. So we're going to scan the sun in one direction. In this case, in the right ascension direction. So everything that we're going to build is in time the sun, an image of the sun, but it's not an instant image. It is really scanning at some speed, particular speed, and then we can, well, we have to reconstruct an image from that. Is it okay? This is the most difficult part to understand. I hope so. Yeah, so I just have to mention, so this is really build your own, so I don't have a 3D printer, but if you have, you can actually print it yourself. The parts are available. The only thing that you have to buy is the optical kit, because, yeah, I don't think that you have the material at home to build your own lens. I don't. So if you don't have a 3D printer like me, you can actually buy this from this supplier, and ask them gently, and they provide a code, a discount code, which is available until the end of the month. So if you use Devox 2023, you get 10% off this. So yeah, really nice people, so do that. So software. So the official software again is called INTI. It's open source, it's licensed under GPL, this is where you get. And, oh gosh, it's written in Python. Well, actually, no wonder, because for most of science-related stuff, it's Python everywhere. I'm a Java guy. I've been working in Java for 20 years. I do Java. When I look at Python code, I just don't understand, right? So I took this, and I didn't find any. Basically didn't find the sources in the beginning. Now they're available because of discussions with me in particular. Like, but the Python stuff is working. It is the official thing, so use that. But one of the problems, typically, if you want to use Python and distribute that, is that packaging something for a user like Windows, you get a 1 GB archive just to do that, right? So not super cool. But there are different problems with this. So I decided to work on a project called JSol'Ex, and because I'm a programmer, I'm not super, I don't have intuition how to choose names, so I just put J because it's Java. And the goal when I started this project is to understand how, from this device and these slits, how can I actually produce an image of the sun? It looked like magic to me. Like, I didn't understand at all how it was working. So I used INTI, I was like, okay, it works, but I don't understand why. So it would be a good exercise for me to try to build software. The second aspect was, I've been working on Java for 20 years. I've worked a lot into tooling. So Groovy is a language, but it's tooling, Gradle, tooling, Micronaut, it's tooling, frameworks, tooling, etc., etc. But can I write an application? Like, I had never written an application for almost all my life. So writing an application is something very different. The focus is very different. So can I still do that? It was also a technical challenge for me. Like, can I do that, and can I, understand enough how it works? One other aspect is that I thought it would be a good exercise for me to understand some newest stuff which was shipped recently in the JVM, like the vector API. Looked like something that I could use, like to accelerate treatment, etc., etc. So, yeah, let's try to do that. And the last point is that if you look into the what is available, in science, actually for Java, there's not much. Like, especially in astronomy, there's not much. And I wanted to start a project and show that Java is actually very capable in that direction. So yeah, I have a complete blog post about that backstory if you're interested in that. So JSol'Ex is actually written in Java, Apache, open source, you can do that. But you can see already a benefit, like 50 megabytes installer, and you're done, right? So compared to 1 gigabyte, that's already cool. So the technology stack that I used, JavaFX. I had never programmed an interface ever. Like, I am not a UI designer or whatever, but I remember 20 years ago, AWT or even before, I didn't want to go that route, so I looked at what is the latest in Java to do design desktop interfaces, and that's JavaFX. There's a CLI version of that, so I'm using Macronaut to do that. I wanted to use Java modules, so modularity. JLink and JPackage are really super nice just for packaging your application, optimizing it, shipping it to the user. So 50 megabytes, that's the result of JPackage. There is experimental support for building native images of the applications. And of course, I use Gradle for building. So enough talking, let's show a demo of what it does. And the first thing I'm going to do is to show what I had to do. So when you capture with a camera like that, what you get is not a typical video file. What you get is what we call a SIR file. And this format is used only in astronomy. You cannot find that. So there were no decoders in Java. So the first step I had to do is actually to write a decoder. And once you do that, well, this is my first ever JavaFX interface. Please, if you're a JavaFX expert, help me contribute some pull requests, right? Because I'm really bad at UI. But that was the first one. So we're playing this video, and you see that the frames are coming, and this is what you get when you actually get this video from this device. So what you see is something which is growing, and you have that line in the middle, and that line in the middle is the H alpha line. So what you see is the spectrum, and it's actually a window of the spectrum. And then it grows because, remember, we are scanning the sun. So when you are at the edge of the sun, you see nothing, and then it grows, and then it's going to reduce again. So now I'll give you that, and give me a picture of the sun. How do you do that? Well, that's what I wanted to answer as a question. So I tried. And I came up with this project called JSol'Ex. So now, let's open this JSol'Ex thing and see how we can process an image like that. So basically, you select the file, and you have some options like selecting the line that you're working with. You have things like I want to auto crop, etc., etc. But let's just do the simplest that you can do for now, like what I call the quick mode. And this is going to build the reconstruct the image, right? So this is the raw image, which is reconstructed line by line. And then you have something which is processed. And maybe if you have good eyes, you can already see that this one is not a perfect circle, and this one is. So you can already imagine some of the problems that we have. And we can actually zoom into the image, look at some details, etc., etc. So there are many things happening already just for that. So that's the quick mode. But what is more interesting is that you can actually do something which I call the full process. And then we're going to generate a lot more images. And when we do that, so you have what we call the continuum line. So this is what you would see. Again, don't do that with the naked eye. Never, ever, right? Even with aluminum paper, whatever, it doesn't work. Use glasses specifically for watching the sun. But if you had these special glasses, this is what you would see with these dots. And this is from the same video. Like just with this single video, we can produce this image, but also an image like the colorized one, or this one which I like also, which is the negative one, where you can see a bit more what is actually moving up. Like you can see, yeah, the difference in the levels. Of course, we produce this Eclipse version, and something which is interesting. So this is not real colors, but again, this is science. What you have there is an image of the sun where you have some red parts and some blue parts, and this is the Doppler effect, right? So what you are seeing there is actually the real movement of the sun. So it is the same, effect, Doppler effect, yeah. Same effect with the car. When the car is coming, you have a sound, and when it goes, the sound is, yeah. I don't remember how you say that in English, but sorry. But this is exactly the same effect, except that you have in the sun. So when you see the red parts, actually it's moving in the opposite direction, and the blue part is coming in our direction. So you can produce that just with this device using this single video. So that's kind of interesting. And then the last one that I'm producing by default is this image where you can actually compute the orientation of the sun and put a grid. And this is actually quite useful also if you want to say, okay, I have discovered this spot at this coordinates. Well, you have that directly with this. So how does that work, and how we can see that? So I have this, what I call this spectrum debugger, and what you can see there is basically the video image by image. So you can actually move in the video, and it shows things that we have to do to make it work. So when I move there, for example, this line, the red line, is actually something that we have to detect, which is the line corresponding to the spectrum line. So it's not a straight line like you would typically expect if you have a spectrum. Because of the design of this JSol'Ex, there are some optical aberrations that you have to figure out. And one of the first things I had to do was actually to determine how we can compute this line, which is actually a second order polynomial. So we can actually figure out, oops, shut up please. We can figure out that line, and once we have that, we have done the most difficult part of the work. So I actually was kind of naive when I started this project because I didn't know how it worked. And I don't know if I asked you how you would do that if you had to reconstruct the sun image, but when I started, I was like, okay, let's do this video, compute the average of basically each line, and that gives me 1 pixel. So when I have one video, I squeeze it down to a single line, and then boom, 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 I'm going to reconstruct everything. That's not how you should do that, because despite the fact that this is black, actually the signal in there. So everything that we care about is within that dark line. So you have to identify that dark line to be able to reconstruct an image. So when we're going to reconstruct the image, basically what we're going to do is what you have in the bottom, like flatten, like correct the distortion, and then use exactly the line in the middle of this black line and nothing else. And that's what is going to be used to reconstruct this image. Is that fine for now? So if my laptop is not too fast, we can actually see that in action. So maybe I should choose a bigger file. Like, so these are all my test files, and I have many. Let's take a good one for now. This one, and I'm going to check one option, generate debug images. So when I do that, you may see the reconstruction in action. So yeah, it was super fast. That's Java being too fast. So it was basically reconstruct the image line by line. But when it does, what you get is this. And you see that we have defects like that, those lines there. And the defects like these vertical lines are actually something that you have to also fix. And this is actually, or maybe you don't see that much on this image. If I zoom in, oops. If I zoom in, maybe it's more obvious for you. Can you see those lines? Right, vertical lines. So these are actually, it's dust that you have on the slit. So as soon as you have dust, well, this creates this kind of lines and you have to fix them. So again, how would you do that? I'm curious if you have ideas. But basically what I did is an algorithm which you can configure there, which I call the bending correction. And my idea was to take all these lines, widen that, and say, okay, I take the average lightness of all these lines, and now let's look at this particular one, and if its average is less than the others in the band, then we have to fix that and raise the level. And when you do that, well, you can actually fix most of it, and you get an image which is corrected, right? So again, you have to parameterize some algorithms like this one, the number of bending corrections. So my slit is actually something that I have to change because apparently there was a defect at the when it was produced. But I have to change it. But it forced me to actually design something which can fix that, right? So that was interesting. Again, I want to show you some of the problems that you can have when you design some things like that. So let's look at one image. Where is it? Yeah, truncated disk in this one. Okay, so I kept the debug images, and that's super interesting. So because it shows you things that you have to do. So this is the average image of the whole video, where we're using that to compute this spectral line. Then we do the reconstruction, but this is what you get. This is not a circle, right? So this is not a circle, despite that this is the sun. And this is just because the speed of the scan can depend. And depending on the speed and exposure time, etc., of the camera, you get something which is circle or not. So you have to correct that. And to correct that, you have to detect the edges. And then, so that's this, detect the edges. And then once you have that, you have to basically perform an ellipse regression. So compute what ellipse is represented in that and fix that so that it becomes a circle. And doing that was not easy at all. Like, I had to read papers about ellipse regression, so lots of math, things I didn't understand at all. And interestingly, I used ChatGPT to help me understand the papers. Like, I had these papers, I was reading that, saying, okay, I think I understand, but this part, I just don't get it. And I asked it, can you help me understand this? What does it mean? And well, actually, AI was super helpful to me just to design and understand. And I could, in the end, implement this algorithm which detects the ellipse and then show that. And once you have that, you can fix it and get a circle, right? But the math behind that is super complicated. And the other thing is that if your edge detection is not right, then the circle that you get is really wrong. Like, it is super sensitive to outliers, this algorithm that I implemented. So as say that I have one red dot, which is inside, then it would totally change the shape of the sun. Like, it would not be a circle anymore after the correction. So something that you have to be aware of. Last thing I wanted to show you is how you get basically these images like the video that I showed you, because by default it doesn't produce anything. So the idea with this program is to do something simple, like you take this do quick mode, and you get some images. But the images that we produce are basically the image of the sun at this particular wavelength. But then you can type in some expression language there. Like if I do image 0 and run that, so I'm going to close the previous images. So you get the image with what we call the 0 shift. So you are in this red line. So this is the image that you get if you reconstruct using that red line. But what is interesting is that if I move 10 pixels off that, I'm getting something different. So it's going to rebuild, and then we are in what we call the continuum. So this is how you get this image of the sun in the chromosphere, in this case, instead of being in the H alpha line. So you have this line, and then you just move some pixels up or down, and then you're seeing something else. And you can actually use this language to produce some animations. So I can do something like range equals range from -10 to 10. Then I'm going to produce a corrected image. So say I'm going to do, so Clary is one of the contrast enhancement algorithms. So I'm going to do this, which takes some parameters. So if I do that already, it's going to work, and it's going to produce all these images and show me all these images. And there they are. So if you move there, you can see the different images which are produced. But then we want to have this animation. So let's create just an output section saying that I only care about that. And I'm going to create an animation. Animation. The of corrected. And I can run that. And it's going to use the encoder to generate this video. Right, and then you see all that. So basically, it's a mode which is an expert mode where you can design your own scripts to make it easier to build some solar images. And in the beginning, I didn't design that specifically for this animation, but for one particular use case, which is the helium line use case that we had before. And for that, I need to switch back to the spectrum debugger, and we're going to use a video which is called the helium line. Take this video, and when we look at the frames, there is one dark line, but the line that we care about, the helium line, is actually not a dark line. It is a bright one, and we only see it if and only if we adjust the contrast. So increase the contrast. And I'm going to move towards the edge of the sun, and you can see that coming already, right? So there you can actually click, and it's going to provide you some details and say, okay, actually, yeah, again, fix that bug if you're into JavaFX, thanks. So it tells you, well, you have to shift about 60 pixels to get that line from the dark line. So now that I have this information, I can go into my program, select this video, and then I'm going to use this custom mode, which image math, and I'm going to select this script, which is called the helium processing, and I just have to use these parameters there and tweak those parameters. So I can share this script with other astronomers and basically say, okay, I'm interested in that. The rest is just magic to make that image happen. And if you're interested in that, talk to me after. I can explain what it does in details. So let's replace this file, run. I don't care about the other images. Run the script, and it's going to produce an image which is not from a dark line, but from a light one. And there you go. you have a picture of the sun in helium line. And if you're not happy with the result, like I'm not in this case, I just don't want to use the one with the background being removed because actually it creates some artifacts. I can run the script again and see the result immediately. And in this case, we can even see some protuberance which are specifically in the helium line. Okay, let's go back to slides because I have 5 minutes left and maybe questions. Why are you? So again, what the program does is basically this kind of things. So geometry correction, ellipse fitting, etc., etc. Then it has to deal with some things like the blurry disk, or if you use calcium in particular, the calcium is very difficult to process, like to figure out the edges of the sun when you process that line. There's this dedicated language, expression language, which is really simple. It's not Turing complete. You cannot do for loops or whatever, but it's really nice to do that. And basically, what I wanted to show you is that, like, first, going back to this and doing something which is out of the work with your passion is super fun. Like, I really enjoyed that exercise. However, I really suck at math. Like, I am fighting with all those papers, trying to understand this cryptic, equations that you have, like converting that to an algorithm. Oh my God! Like, what does it mean? It's super complicated, but AI can help. So do not hesitate to do like me. Yeah, the last point, Java modules. Okay, so I work for Oracle, but I shouldn't say that. But it was a nightmare to make it happen with modules. So basically, because not everything is a module, you have problems like automatic modules and patches that you have to make just for the application to build. So not super happy with that, but unfortunately, to make the JLink and JPackaging work, you have to use that. So that's super fun. And my conclusion is that just with this device, basically, you come into real science. So you can really contribute to what we call the pro and amateur astronomy collaboration. And if you go to this site, which is an official site from the Meudon Observatory in Paris, they have a section dedicated to images taken by amateurs with the JSol'Ex. So this is professional images which are actually used by professionals to study the sun. So you can contribute to science using this device. So really, come and do it. Just the resources again, and I have just 2 minutes for questions. Any question? Yeah?
So, is magnetic, you made a picture of magnetic as well, right?
Yeah.
Visible light?
It is not directly visible light. It is that the light is polarized. So we are using a side effect of this device, which is basically that if you put filters like these 3D glasses, so you have one eye which is polarized in one direction, and then you have a filter for the other eye which is polarized in the other orthogonal direction, and basically it lets you see the direction of the light, like the polarization of the light. So we don't really care about whether it's visible or not. What you care is that you're going to compute this polarization of the light from the difference of 2 films. 2 different movies, yeah. So you basically have to change the filter between 2 sessions. Okay, so time's out. If you want to take a closer look, don't hesitate to come after. And yeah, thanks for attending.